In this video, we are going to look at how we can make use of spatial coordinate systems to manipulate geometric entities in 3D space. Coordinate systems allow you to uniquely specific points in space. Note that in this video, when we refer to a point, we are referring to a location in space. We are not referring to point objects in Mobius. There are many different types of coordinate systems for different purposes. In this video, we will be focusing on the Cartesian coordinate system. The Cartesian coordinate system uses a sequence of numbers to uniquely determine points in space. Cartesian coordinate systems can be 2D or 3D. In many of the slides we'll use 2D examples, since it is easier to visualize. You can simply assume that the z-coordinate is 0. In these slides, the x-axis is shown in red, and the y-axis in green. When working in a coordinate system, there are typically two possibilities. You can use a global coordinate system or a local coordinate system. For the global coordinate system, there is only one. It is the absolute frame of reference to which everything else is related. However, sometimes it may be awkward specifying certain operations in the global system. Usually this is due to the fact that the geometry is not aligned to the axes of the global coordinate system. In such a case, a local coordinate system can be defined as a convenience. The local coordinate system can be placed at any location and at any orientation. The local coordinate system is defined relative to the global system. For defining a local coordinate system, at least one point and two vectors are required. The point defines the origin. The two vectors define two axes. The third axis is not required, since it can be derived from the other two. In this case, we will assume that the two axes are the x-axis and the y-axis. You will notice in the example that the origin and axes are defined using coordinates and vectors in the global coordinate system. For example, the local x-axis is set to 0, -1. Thus, the local x-axis is pointing down in the global coordinate system. Every point now has two coordinates: a global coordinate and a local coordinate. In the example, the point P1 has coordinates 2, 1, in the local system, and 5, 4 in the global system. In addition, more than one local coordinate system can be defined. The different local coordinate systems are all placed relative to the global system. It is also possible to transform geometric entities from one system to another. In the example, we have created a rectangle in the global system. This rectangle can then transform to the two local systems. Here we can see how the rectangle is translated and rotated. The coordinates of the points in the global and local systems are the same. For example, in the global system, the top right-hand corner of the rectangle has global coordinates of 2, 3. In the local coordinate systems, the top right-hand corner of each rectangle also have local coordinates of 2, 3. Once we switch to 3D, we need to orientate the axes of the global coordinate system relative to the real world. The orientation of the axes is a convention. In urban domains, the z-axis is by convention pointing up. The x-axis is pointing east, and the y-axis north. For the 3D coordinate system, let's look at the default planes first. A series of 6 default planes can be defined as local coordinate systems. XY plane is typically the standard plane in many systems. A local coordinate system defined on the XY plane has axes parallel to the global coordinate system. For the y-axis, the diagram shows how the axes are flipped, so that the local z is now pointing down. These two diagrams show the zy and yz planes. In each case, you can see how the axes of the local system are aligned, but flipped. The diagram for the ZX and XZ planes are similar. In addition to the default planes, a local coordinate system can also be created in 3D at any location and orientation. In order to lock the coordinate system in place, 1 point and 2 vectors are required. The point defines the origin. The 2 vectors define 2 of the axes. Placing such a coordinate system is usually done relative to some existing geometry. Let's have a look at a few examples. The most common way of placing a local coordinate system is by aligning it with an existing polygon in the model. In this example, we can see the local coordinate system is aligned with a polygon that is sloping at an angle. 2 versions are shown, one where the origin is places at one of the vertices, and another where it is placed at the polygon centroid. In such a case, the z-axis is typically aligned to be parallel to the polygon normal vector. Another common case is aligning a series of coordinate systems along the length of a curve. In this case, the z-axis is usually aligned to be tangent to the curve. However, note that this only locks one of the axes. The coordinate system can still spin around the curve. In order to lock the coordinate system, one more axis would need to be defined. Finally, a similar case to the curve is aligning the coordinate system at a series of vertices along a polyline. In this situation, it is often necessary to carefully orientate the local coordinate systems. The local z vector would have to bisect the angle between the previous edge and the next edge.